back to you on, puts us back to you on Thursday. And also the homework. Reminder that this week, the Thursday lab is the one that does what the Friday lab did last week. And so I'll be there if you have questions. But it's not required that you attend the Thursday lab. But Friday lab will be doing a full-on in-class session that is the same as what we did in lab last Thursday. And then the total lab will be a double lab, and that will be due a week from either Thursday or Friday, depending on which lab section you're in. What I'd like to do today is take a look at the rest of the subjects from chapter 17, which is on pressure waves. And so recall last time we were looking at something like this. Where we have a sound wave that is produced by a simple harmonic motion source. That sound wave sends off a series of compression and rarefactions of the air in the room. And then those eventually get to your ear, and then your ear, if it is a maximum compression, will experience a larger force, which will be delta P plus P atmosphere times the area. And then on the back side, you'll have just P atmosphere times the area. So this is just the force of the air, pressure times area. A is the area of your eardrum on the inside part of your ear versus the outside part of your ear, and that generates a net force. When delta P is a maximum, that delta force will push this way. When delta P is a minimum, then this will be minus delta P, then that'll give you a net force which will push that way. And so that is then what causes the simple harmonic motion vibration of your eardrum. And so as this occurs, we could model again the eardrum as being a mass on a spring. And using that model, we know that there are certain natural frequencies that that system will want to vibrate at that will be a larger vibration. But if you stimulate it with frequencies that are away from the natural frequency, you'll have a reduction in the response. And so in other words, you won't hear it as well. It won't sound as loud. And so here's a range of audibility for the human ear. Typically, the human ear in terms of frequencies, the frequency range is about 20 hertz to 20,000 hertz. Anything above 20,000 hertz would be considered hypersonic, and dogs could hear something that's above 20,000. But typically, even the best of us, in terms of high frequency hearing response, won't be much better than 17 or 18,000. And that tends to drop rapidly with age. Once you're above 25, a lot of the high-pitched sounds that you were hearing as a teenager are going to start to evaporate, and slowly but surely your range of hearing in terms of the blue region here will shrink in this direction in terms of what it is that you're able to hear. And so what I wanted to do here in this first example is to show you how sensitive the human ear is to vibrations. And so we can do that with the handout that you may have already gotten. I'm just going to go over that here with you. What we have seen before is that for sound vibrations in a fluid, we can write that the velocity is the square root of the bulk modulus divided by the area. And we defined the bulk modulus before as minus delta P, which is the difference in pressure that causes this fractional change in the volume. And so if we're then talking about a compression wave, like this, where we have regions of higher compression, then what will happen is that the molecules will move back and forth with simple harmonic motion. Then they follow a relationship that looks like, we call this y, although it's not, it's in the same direction as the direction of wave motion. If we call it y, then y would be a, where a is the maximum amplitude times the cosine of kx minus omega t. So this is the maximum particle distance from equilibrium, but in the compressed wave direction. So let's be really clear that this is for a compression wave and not a transverse wave. Or what in the book is called longitudinal. I don't like it because I can't spell it. Longitudinal. And so if we write this then in terms of delta P, then we can think of the change in the volume, delta V, that is associated with a certain displacement y, like that, in relationship to the motion of the wave, which would be in relationship to the total volume. And so you have a fractional change in volume divided by the total volume. And so we could think of that then as being the partial of y with respect to x. And if we write this as delta y over delta x and then take the limit as the fractional change in the volume goes to 0, we can then write that the difference in atmospheric pressure is equal to the bulk modulus times the partial derivative of y with respect to x. So if we take that partial derivative here, we get a minus Ka times the sine of Kx minus omega t, and then we get a pressure variation, delta P, and this is the one that we've been using in class. That's equal to what we could call here delta P max. And here we see that there's an actual functional expression for delta P max in terms of the maximum amplitude. Where A is the maximum distance from equilibrium that the particle moves as it vibrates back and forth with simple harmonic motion. So we can combine that together. That gives us delta P max is equal to BAK. And then we can write the bulk modulus again, because the bulk modulus divided by the density is equal to the velocity, the bulk square root of that. The bulk modulus then is equal to V squared rho. And plug that in here, and we get the delta P max is equal to density times V squared times A times K. Now we can do a little bit of manipulation of that and solve for A. If we do, we get A is equal to delta P divided by rho omega V. Now the way this was done, and it's just kind of a convenient way of rewriting the maximum amplitude in terms of delta P. Okay, so this is how the maximum displacement relates to the pressure difference that is causing the disturbance. Remember, you can either talk about particle displacement in the medium, or you can talk about pressure differences. And what I preferred to do was talk about pressure differences. But here, I'm trying to tie it together so you can see how those two relate to each other, how the pressure difference and the particle displacement for a compressed wave are related. And so here, we can take one of the v's and turn it into an omega over k, and then leave the other v. Okay, so we have a rho v times omega over k times a k, like that. Then the k's cancel, and that gives us this relationship for the amplitude, delta p divided by rho omega v. Now, how does this relate to the minimum intensity sound that you can hear? Well, if we go back to this picture here, we see that this is your threshold of hearing. And so associated then with your threshold of hearing, this is the minimum sound that you can hear. And so at 1,000 hertz, the minimum intensity is equal to 10 to the minus 12 watts per square meter. And so that's a factor of 1 trillion times lower intensity than the intensity of the loudest sound that you can hear without doing ear damage, which is about 120 decibels. And so with a minimum intensity of 10 to the minus 12 watts per square meter, we define that as being 0 decibels. Okay, so 0 decibels then doesn't mean 0 sound. It just means that this whole thing is related to the minimum intensity of sound that the human ear can hear. And so and there's a calculation that's necessary to do this that I'm going to leave out. But when you do this calculation for intensity in terms of maximum amplitude, what we get for the delta P is 2.5 times 10 to the minus 5 pascals. So associated then with 0 decibels, we have a delta P max that's just 2.9 times 10 to the minus 5 pascals. So if we relate that to atmospheric pressure is about 10 to the plus 5 pascals. So we're dealing with a factor of 10 to the 10th power difference between atmospheric pressure and the variations in atmospheric pressure that can produce the sound that we can hear. So this is giving us a clue that the human ear is remarkably sensitive to small amounts of vibration. And so if we go down then and we work this through with this value for delta P max, and this is something that can be derived from this intensity. But let's just say that we're going to jump through that without doing the derivation. Then what we get is the maximum distance of particle motion is going to be equal to delta P divided by rho. Here rho is the density of air, 1.26 kilograms per cubic meter. That's about a little more than 1,000 the density of water. Times, and this is at 1,000 hertz, so omega then here is 2 pi times the frequency. That's 2 pi times 1,000 times the velocity of sound, which is 340 meters per second. And when we work this out, we get that with the faintest sound that you can hear at 1,000 hertz, the eardrum is only moving about 1/100th the diameter of an atom. That's how sensitive the human ear is. It can pick up vibrations that are only 100th the diameter of an atom. Amazing. And so this is why we should be careful with our hearing. It turns out, unfortunately, that men seem to be more vulnerable to high-frequency hearing loss than women. That doesn't mean that women can't get it, but men seem to be more susceptible to it. And so listening to vibrations that are 1 trillion times more than the most sensitive vibration that the ear can hear. Just imagine if you did that with a delicate little watch spring, and then you hung a car from it. What is that going to do to that spring? And so that's the reason why you need to be cautious, wear earplugs if there's excessive amounts of noise to preserve your hearing so that you can still hear something when you get to be old. Okay, so are there any questions about this example? Okay, the next thing I wanted to look at is a little more about the quality of sound. We saw before that if you hear the same note being played on different musical instruments, sounds very boring on a tuning fork. But it's a little more interesting if you add in a few of these overtones, a few of these higher frequency harmonics. So in each case, you're hearing the same note, but with different relative contributions to the overtone. All the same note, but the overall shape of the wave pattern has been adjusted. And so this is what gives rise to the quality of the sound that you hear. And so when you turn up the bass or the treble, when you're listening to music, what you're doing is enhancing the higher frequency overtones or the higher harmonics versus enhancing the lower harmonics if you want more bass. And so the question is, one of the questions that we could ask is, does that sound good? Not so good. Does this sound okay? Maybe a little better. Some of these sounds sound okay together. But some of them just don't sound very good together. And so if you put that all together, we might wonder, well, why does this sound so incredibly good? Isn't that wonderful?
No.
Well, we're not sure, but it seems as though there are mathematical harmonies that sound better. And they tend to be in integer ratios, small integer ratios. And math harmonies that are in large number integer ratios don't sound so good if they're consecutive. So in other words, 4 or 5 to 3 would tend to sound good. But 19 to 18, not so good. Okay, and so something like that. That one's particularly bad. If you go to just an octave difference, that's not too bad. But you know, there are certain ones that just aren't as good as others. And so this is kind of a mystery, but it appears as though what are called Fibonacci numbers seem to have something to do with this. And Fibonacci numbers are numbers in which you take the previous two, actually this one appears twice, 2, 3, 5, 8, 13, 21, These numbers seem to appear very often in nature. And and ratios of these tones sound good. But you also find that you might have a flower that has 3 leaves on it, or 5. But a 4-leaf clover is considered very lucky because it's very unusual. So you get these kinds of ratios are found in repetitive patterns for plants. They're also found in the ratios, say, between the length of your finger and the distance to your second joint. They are found in the distances that are associated with your hand versus your whole arm. And these kinds of ratios as proportions look better architecturally. So it appears as though there may have something to do with an optimization of resources that allows for these numbers to keep appearing in nature the way that they do. But it's a little bit of a mystery exactly how the resources are optimized or why nature tends to favor these kinds of ratios. But if you were to look at an oscilloscope and look at the different wave patterns, you wouldn't see much difference between them. There seems to be some selection process that goes on that it may have begun with, say, mating calls. If you sent out a combination of sounds that sounded good, then you would reproduce. If you sent something out, no, that doesn't sound so good, you don't reproduce. And so perhaps we've attuned our senses to the kinds of frequency ratios that have allowed for us to survive. But it's an interesting puzzle and not fully well understood, but does appear to have something to do with optimization and making the best use of your resources for survival. Are there any questions about that? Okay. What I wanted to look at next is what happens with auto-tune and how you can change the combinations of frequencies in such a way as to produce pleasing sounds.
Yeah, I sing.
In the nebula of my soul.
Okay, I'm not great.
But now I find her heart
Just a little bit.
is like a big black hole.
All right, I'm terrible. But here's what I'm wondering. If digitally you can remove red eye, smooth over wrinkles, make people look thinner, then why don't we have the technology to make me sing better?
We can fix Neil.
This guy invented a way to do it.
You can fix Neil's pitch. He's still gonna sound like Neil, though.
Electrical engineer and inventor Andy Hildebrand designs pitch correction software. He calls it Auto-Tune.
Pitch correction. Is that a euphemism for fixing bad singers?
Yes, we fix bad singers.
I visited Andy at Antares Audio Technologies in Scotts Valley, California, where he and engineer Justin Malin showed me how it works.
Great. There you go. You did that.
That wavy line represents the exact frequency of my voice. This line shows where a perfect A should be. So, not too bad.
He's right dead nuts on in tune. Look at that.
So how does a computer know that?
When you hear A, you're hearing 440 vibrations per second.
So somebody at the beginning of time said 440 vibrations per second is an A.
A.
Okay.
A.
So if you sing or play a pitch at 440 cycles per second, the computer calls it an A, and it rests on this line. B flat would go on the line above it. G sharp below. And so on. When you're out of tune, the notes don't fall so neatly on the lines of the grid.
That's awful.
Well, it's creative. It's creative, okay?
Those lines are me singing the word super. My pitch is all over the place. If anything, it's closest to this note here.
Neil, you sang an F, which normally is okay if you're in the key of F, and we're not. So we moved your F to an E.
Supernova. So Justin gently nudges it down to where an E would be.
Supernova. You're changing the frequency of the sound that came out of my vocal cords.
Actually, guess.
Christmas, Christmas.
Changing pitch isn't new. You can change someone's voice by fast forwarding on a tape recorder. But you sound like, well, a chipmunk. Pitch correction software lets you change the pitch while keeping the essential tone of a voice the same. And so, although few engineers are willing to admit it, pitch correction software like Auto-Tune has become an indispensable tool in most recording studios.
It's been used by a lot of people. Madonna.
Celine Dion. Reba McEntire uses it live.
Starting over again.
You're telling me a singer can sing into a microphone a bad note and out the speakers comes a good note?
Yes.
Now that's evil.
To modify something isn't necessarily evil. My wife wears makeup. Is that evil? Is that okay, honey?
Evil or not, the recording industry kept Auto-Tune on the down low.
The secret popped out of the bag when Cher did Believe. I couldn't believe it.
Rather than gradually and naturally reaching up to each note, like this, Cher's producer forced Auto-Tune to jump suddenly from one pitch to the next.
There's some knob that you turn.
Yes. And we can turn this knob to 0, which means move instantaneously to the new pitch. And so if we do that, your voice would sound like this.
But now I find her heart. Did you plan for people to use it that way?
No.
Oh, okay.
No, I didn't think anybody in the right mind would ever use it.
Well, a lot of artists do. But it's mostly used to tweak out-of-tune performances, a kind of cosmetic surgery. In my case, though, more like triple bypass,
Try to change this to the key of C. But
moving the traces of my voice up in pitch or down. Justin coaxes me into tune. It took several hours,
of my soul.
How well did it work? You be the judge.
Our love was like a supernova, the nebula of my soul. But now I find her heart is like a big black hole.
It's a lot more pleasing.
I thought the first one sounded pretty good myself. I don't know. Kidding aside, there's no substitute for training or talent.
If the singer doesn't have a good tonality to their voice, we're not going to make that better. Do us a favor.
So, just a couple more things about the Fourier transform of these different combinations of harmonics. With a tuning fork, you just have one frequency, one single frequency. In a clarinet, you have this combination of frequencies. But with the n=1 harmonic being the largest amplitude, and the other ones basically then just modulating the waveform. But you see that there's a certain prescription for how to make that particular sound. And so that's what has been programmed into the synthesizer, is that combination of frequencies that makes a particular musical instrument sound the way that it does. But the reason that this sounds so cheap is that the combination of harmonics is also a function of frequency. So if you have a clarinet that's playing a higher pitched tone, then you may get something in which the different harmonics are a little different than what you hear at that one frequency. And so it's an oversimplification to say that there's just one set of harmonics that works for every frequency for a musical instrument. But at a typical frequency, we see that this is the kind. And so this is what you do when you do Fourier transform, is you basically change it from something that's a function of time to something that's a function of frequency, where you're looking at the amplitude as a function of the frequency or the harmonic content versus looking at it in, as it progresses in real time. Notice here for an oboe, unusual instrument, and this is a rare exception where it actually has a higher amplitude in the second harmonic, but that is usually not the case. So the next thing I wanted to look at, we've already talked a little bit about sound intensity. And so what I want to do is relate that then to the decibel scale. Now, we can have a sound intensity in watts per square meter, or sometimes it's also written in watts per square centimeter instead of watts per square meter, but for our purposes, we usually use MKS units. So our intensity then would be watts per square meter. But what we saw in that previous example is that for the faintest sound that you can hear, the amplitude is only something like 1/10 trillionth the amplitude of the loudest sound that you can hear. Okay? And so that would be more on the order of 1 watt per square meter. And so the range in intensity for hearing a sound is something like 10 to the minus 12 watts per meter squared. And that was involved in our last calculation where we did the amplitude, and it was just 100th the diameter of an atom. To the threshold of pain, which is 1 watt per meter squared. It should be 1 trillion times louder. So you get this if you're sitting right next to a loudspeaker at a rock concert, or maybe with a DC-10 coming into land and you're standing right below the airplane as it's coming in. This corresponds to what we call 0 decibels, even though it's the faintest sound that you can hear. But in order to keep this all on a reasonable scale so that we don't have such humongously big numbers, we use a logarithmic scale. And so 1 watt per square meter corresponds to 120 decibels. And so we need a mathematical relationship then that compresses 12 orders of magnitude into something that is just a more reasonable set of numbers. And so this is the same kind of thing that's done with the Richter scale. You have a magnitude 6 earthquake. That only has 1/10 the magnitude in amplitude of a magnitude 7 earthquake. And that's only 1/100th the magnitude and amplitude of a magnitude 8 earthquake. So the magnitude 9 that we were looking at with Alaska, that had, versus a magnitude 6, that would be magnitude 7, 10, 100, 1,000 times the amplitude. And it's 30 times the energy increase for each increase of 1 in Richter magnitude. Okay, and so that's the idea here then, is we want something that has a logarithmic scale so that we can squeeze something that has a larger range of values into a set of more reasonable numbers. Any questions so far? Okay, so the way we do that then is we write that our magnitude, beta, so this is our decibel intensity, so the units then are dB. It's equal to 10 times the base 10 logarithm of I over I naught. Where I naught here is our threshold of human hearing. That's the minimum intensity sound we can hear. So, but that's the minimum intensity sound that you can hear at what we would say is near the peak frequency at which we hear the loudest sound. And so if we go back to our table of hearing responses here, we see that we get a peak response down in this area, which is on the order of a couple of thousand hertz. Okay, so this is really what we're talking about then. And so here, this is 10 to the minus 16, but it's watts per square centimeter. Okay, so a square centimeter is equal to 10 to the 4 square meters. And so this is the same thing then. 0 decibels on this thing in watts per square centimeter is the same thing as 10 to the minus 12 watts per square meter. This 10 to the minus 14 would be 10 to the minus, 10? This would be 10 to the minus 6, etc., as we go down. Okay, and so what this gives us then is a relative scale that's based on our ability to hear as being 0 decibels. So in other words, if I equals I naught, then we have beta is equal to the base 10 logarithm of 1. But 1 is 10 to the 0. And so using the basic properties of logarithms, we can say that the log of a to the n is equal to n log a. Okay, and so if we write this then as the log of 10 to the 0, that's going to be 0 times the base 10 logarithm of 10, which is 1. Okay, and so that's 0. So that's what gives us 0 decibels by taking the log of 1, which is 10 to the 0. Okay. But then if we go up to the maximum threshold of human hearing, then we're up here at 1 watt per square meter. Then beta, for that value, is going to be 10 times the base 10 log of 1 divided by 10 to the minus 12. The units will cancel out, and so that'll be 10 times the base 10 logarithm of 10 to the 12. But then, using this basic property of logarithms, we can write this as 12 times 10 times the base 10 logarithm of 10, but that's just 1. And so that's 120 decibels. Okay, so that's where what you're dealing with the threshold for pain. Okay, if you have normal human conversation, that might be somewhere around, well, this is 10 to the 10, this would be 10 to the 8, this would be 10 to the minus 6. So for normal human conversation, let's see how many decibels that would be. Then the beta value would be 10 times the base 10 logarithm of 10 to the minus 6 divided by 10 to the minus 12. So watts per square meter are canceling, so I'm not writing in those units because it's a ratio of intensities, and so therefore this is a unitless quantity. And so that gives us 10 times the base 10 logarithm of 10 to the plus 6 power. That would be 6 times 10 times the base 10 logarithm of 10. So that's just 60 dB. Okay, so 60 dB then would be normal human conversation. Heavy street traffic might be 10 to 100 times more intense. So if we go up then to I equals 10 to the minus 5 watts per meter squared, that's 10 times as loud, okay, as this one, as conversation. All right, say here intense. In terms of energy, remember intensity is power per unit area. Don't forget that from last lecture. That's the concentration of power on an area. Okay? And so if it's 10 times more intense and you plug in, well, again, here is beta equals 10 times the base 10 logarithm of 10 to the negative 5 over 10 to the minus 12. So that would be 10 times the base 10 log 10 to the 7. That'd be 7 times 10 times the base 10 logarithm of 10, or 70 dB. So 70 dB is only 7/6 as high of a decibel, but we have to remember it's a logarithmic scale. So what this is showing us then is an increase of 10 decibels is the same as an increase of a factor of 10 in the intensity. So we don't want to be confused into thinking that the intensity has gone up by 7/6. It's gone up by a factor of 10 every time you go up by 1. Just like with the Richter scale. Go from 6 to 7, it's 10 times more amplitude that's associated with it. So it's a lot louder sound. And so if you were at 90 decibels, what factor of intensity would it be versus 60? Good. So that would be 1,000 times a 60 decibel sound in intensity. Okay, and so you go up to 100 then, that'd be 10,000, 11, that would be 100,000, 12, that'd be 1,000,000. So you're talking 120 decibels at the point where your ears are going to be ringing for a couple of days and maybe a little bit of blood starts coming out. That's 1,000,000 times the power per unit area of normal human conversation. But it's all on this compressed decibel scale. Are there any questions about that? Now sometimes you might be given the beta intensity and want to know what the regular intensity is. So what if I told you that the beta intensity was 80 dB and you want to find I from that? Then you'd have to work this relationship in reverse. So far we've used this relationship. Log to the base 10 of a to the n is equal to n log to the base 10 of a. But now we're going to have to go a little farther with this. If we know what the beta intensity is, then the only unknown in this equation is I. Because we know I naught. I naught will always be given. You won't have to memorize that. I'll give that to you. 10 to the minus 12 watts per square meter. Assuming that we're in a frequency range where the ear is responding well, which is around 1,000 to maybe 3,000, 4,000 hertz. Okay, so to do this here then, we can say, well, okay, first what I'm going to do is divide through by 10. So we get beta over 10 is equal to the base 10 logarithm of I over I naught. And then what I'm going to do to cancel out the logarithm, because I'm trying to get to the I, which is inside of the logarithm here, is I'm going to do what? What should I do to isolate? Good. Exponentiate. Okay, so we raise it to a power of 10, because 10 to the base 10 logarithm of A is just equal to A. And so by exponentiating, we've undone the damage that you did by taking the logarithm. Okay? And so that's sometimes called the inverse function. The exponentiation function for a particular logarithmic base is the inverse function of the logarithm. Okay? And so what this will give us then is just I over I naught is equal to 10 to the, and beta in this case was what, 80. So that's 80 over 10 is 8 power. Okay, So everybody okay with what I did here? I didn't skip too many steps. I over I not, because if A equals B, then 10 to the A has to equal 10 to the B. So I haven't changed anything that's equal by doing this. I'm just putting it in a form that allows me to isolate and get rid of the logarithm and isolate the argument of the logarithm. Okay, so I over I naught then is going to be equal to here 10 to the 80 divided by 10. So that gives me I is equal to 10 to the 8 times 10 to the minus 12. So that would give me 10 to the minus 4 watts per meter squared. Okay, and so over here this was 70. That was 10 to the minus 5 watts per meter squared. So we see that that in fact is consistent because we're going up by another factor of 10 in intensity. And so we're going from 70 decibels, which was 10 to the minus 5 in this previous example, to 80 decibels, which is 10 to the minus 4. So can everybody go both ways with that? Okay, here's another little exercise. I'd like you to just spend a couple of minutes on this. See if you can knock this off. I'm not going to have you turn it in, but it's a typical kind of a quiz or an exam question. Say that one trumpet has a decibel intensity of 70 dB. Let's find the decibel intensity for 5 trumpets. Is it going to be 7 times 5? 350? No. It's not. What's the most it could possibly be? What if it were 10 trumpets? What would it be? It'd be what? If it were 10 trumpets, it'd be, how much more intensity is that? 80, right. So if it were 10 trumpets, then that would be 80. So we know it's going to be somewhere between 70 and 80. 75. You might think possibly 75 if we're a linear function, but it's not a linear function, it's a logarithmic function. And so because it doesn't relate to a straight line kind of a plot, log x versus x looks something like that. So it's not linear. So I wouldn't expect it to be 75. Go ahead and see if you can find it. There's 2 ways I can think of doing the problem. One way is a little faster than the other. we haven't finished solving it yet, does anybody have a suggestion on how to begin? What would you want to do? Anybody?
I'd solve for I, multiply by 5, and then put it back in.
Okay, you could solve for I, multiply by 5, and then plug it back in and find the new decibel intensity. And so that's certainly a legitimate way of doing the problem. And so we saw before that that corresponded to a 10 to the minus 5 watt per square meter intensity. Okay? And actually what I did in this example is I gave you 10 to the minus 5 and I asked you to solve for the beta. But you could easily work this around the other way, and you could then solve this for the intensity, and you get 10 to the minus 5. You get something like, what, 10 to the beta over 10 is equal to I over 10 to the minus 12. So then I would be equal to 10 to the 7 times 10 to the minus 12, which would be 10 to the minus 5. Then you can plug that back in to this expression, and that would give you beta is equal to 10 times the base 10 logarithm of 5 times 10 to the minus 5 divided by 10 to the minus 12. And that would give you, has anybody done that yet?
6.9.
Okay, good. About 77 decibels. Okay, so that's certainly one way of doing it, and it is a very legitimate way. I wanted to show you one other way you could do it. The other way is to use the fact that the log base 10 of AB is equal to the log base 10 of A plus log to the base 10 of B, like that. And then we can use the fact that 10 times that is our decibel intensity. And so then what we could do is we could just say, well, this is 5 times so this base 10 of log A is going to be, this is basically your 70 dB here. So this is 10 times 7 plus the log to the base 10 of 5. Okay, because this is 5 times the base 10 logarithm. And so that'll give you 77. Just by using the fact that 10 times 70, that's just your original plus however much more you're adding to that. Well, what you're adding to that is 5 times that value, 5 times that intensity. So you knew the original intensity was 70, and so 10 times the base 10 log of 5 is 7. All right, any questions about using that equation? All right, next thing I wanted to look at was beat frequency. Now, when we have a beat frequency, basically what you're looking at are a combination of 2 different tones that gives rise to a composite tone that sounds like it's basically these two tones added together, but in a way that because they're slightly out of tune with each other, they come into phase and then back out of phase again. Okay? And so this usually works, though, only if you have similar tones. In other words, tones that have frequencies that are close to being the same as each other. And so what is this useful for? Well, you might, for example, have a circuit, a timing circuit, and that circuit might have some kind of an electrical oscillation that is a little bit off from the correct value for that time. And so from that information, you could figure out by listening to the beats how far out of tune it is. Then you could just adjust a capacitor or something and bring the circuit into correspondence with the standard oscillating frequency. In a guitar, a lot of times what you'll do to tune a guitar is you'll have a certain string, you'll pluck it, and then you shorten one of the strings by a certain specified amount. And then, by shortening the string by this amount, you hear it go in and out of phase. And so then you adjust the tension. So maybe you go and you've got something that is, say, picking up the frequency off a piano that's well tuned or something. So you know what that basic frequency is. And then you listen for the beats and then you adjust the tension until the two are in tune. And then you follow that process through and you tune your guitar. Here we have a tuning fork, 256 hertz, and here we have a second tuning fork that has a weight on it. It says 256, but I don't fully believe that it's 256 because it's got the weight on it, which is going to give it more of an inertia factor. So which one of these two, the one with the weight or the one without the weight, do you think is going to have the higher pitched tone? Without should have the higher pitched tone because it has less inertia. And so if it's not too much different, then we may be able to hear a beat. So you're hearing it modulate in and out, and then if I take this thing off, then they're totally in phase and the beat goes away. So now they're in tune, that it wasn't in tune before. And so let's see if we can count how many times this thing goes in and out of phase in 1 second. What does that sound like to you? Maybe 12 in and out of phase? 12 of these a second? Trying to be scientific. So how does this all work? Well, when you add the two waveforms together, they go into and out of phase. And so if the frequencies are close, to each other, then we have what's called a beat frequency envelope. And so we have, here's the background tone. This background tone is going to be F1 plus F2 divided by 2. So the background tone that is being modulated by the thing going into and out of phase with itself over a certain length of time is the average of the two frequencies. But the beat frequency envelope, which is what you're hearing, that series of loud and quiet sounds of it going into and out of phase, is the difference between the frequencies. So in this case, let's say FB was equal to 12 hertz. Okay, 12 cycles per second. Because I was just kind of, without trying to time it, I was guessing that do something like 12 times in 1 second. Just maybe that's not right, but let's say it is. And I could probably make it right, by the way, just by changing the position of the weight on here. That would affect how much inertia it would feel, because it would have to go through a larger vibrational amplitude if I put it up higher. If I put it down lower, it's not going to have as much of a vibrational amplitude, and its inertial effect probably wouldn't be as bad. So I could probably adjust that difference in frequency just by moving this weight up or down. But let's assume that I put it at the point where the beat frequency is 12 hertz. And so if the frequency of the unweighted fork F naught, let's say, is equal to 256 hertz, then let's see if we can find the frequency of the weighted fork. And the background frequency. Go ahead and see if you can do that. That's the unweighted fork, 256 hertz. I'm hearing a beat frequency of 12.
So the beat frequency is equal to F1 plus F2 over 2.
Right. So once you found F2, then you can do the background from the average between the two. What are you getting for F1? To 68? Is that a good guess? Anybody getting that? What are you getting? Is that right? Which one did we say had to have the higher frequency? The unweighted one. So this is the unweighted fork. So that has the higher frequency. So what does that tell us about the other one? It's got to be lower, right? So how much lower? 12. Okay, so 244, does that sound okay for F1? Everybody okay with that? Because it's 12 less, and we know that the weighted fork must have more inertia, and so therefore if I'm hearing a beat frequency of 12 hertz, then that means that the weight is reducing the frequency by that amount, by 12 hertz. Now, if I made it too much less, then this kind of interaction, it would kind of blur together. You'd hear so many beats that one would be kind of on top of the other, and it wouldn't be discernible. So the two frequencies have to be somewhat close to each other relative to the size of the original frequency for you to be able to hear this kind of a beat. So you've got to be close, in other words. And so what's our average or background frequency? Good, 250. So this is going to be 256 plus 244 over 2, or 250 hertz. And now, this result can be gotten by doing a sum of the simple harmonic motion interference between these two waves. And this is something that we'll do in Physics 2.8c, because it turns out that beats with matter waves are what particles are. So when you have like an electron, that's actually a combination of different electron wave frequencies that beat. But if you have enough of the frequencies together, then the outside lobes are small, and it basically